All right, what I just got done explaining was that they're going to be given a take-home test. They are allowed to use their notes, and they are allowed to use their book, but they're not allowed to look things up on a computer or ask somebody else to help them. And they'll be given this take-home test today, and they'll have until a week from this Thursday to turn it back in. So, Alan, as far as that, I will send this to you, and you'll have this. You can also have that time, and I think you have a book. I believe you do, but anyway. And then we're going to do a chromatography lab, and what you'll do, Alan, is if you you could actually do some of these at home. You could try some at home, but you may have to just be doing a research paper on chromatography. All right? Okay. Okay. All right. All right, so everybody doing all right? You guys seem a little bit more quiet, or what are you thinking? You're sad because you have to leave here, or is that it? Okay, it's all right. Here, if you're crying, start crying. You got plenty of time. All right. So what I'm going to do is we were talking about this thing called periodicity. And periodicity is a kind of a neat word. If you say it, say, "Whoa, you're pretty smart." And say periodicity is simply what are the kind of patterns that exist in the periodic table, the trends of the periodic table. Okay, let's see if you remember. I did not get a new battery yet for my laser. Dang it. Okay, so it'll work for about 30 seconds here. Do you know any trends right now? The only thing you probably know is that the periodic table is arranged by atomic number, and it goes 1, 2, 3, 4, 5. That's protons, isn't it? One of the original periodic tables was arranged by mass, average mass. But if you've taken a look at the periodic table, you'll see that it kind of is with mass. See, 6.9. But you notice right here. Here's argon at 39.9, and here's 39 less than 0.9. So if the original periodic table said mass is how you should organize them, but the modern periodic table has atomic number. And even Mendeleev, when he did it, somebody wanted to put one in front of the other. He said, no, it just doesn't belong there. And so there's about 3 or 4 or 5 times where the mass is not in order. And so you know about that trend here. You also know that there are 7 periods in the periodic table, and that the first energy level, level is closest. It's the smallest total volume and everything, smallest diameter and everything. And so it would make sense. What is a trend for atomic size as you go down a group or family? What's a trend as you go down? And everybody in this room, I think, should know this one. What is it? And why does it get bigger? Yeah, but the atomic number gets bigger as I go left to right.
More like the atomic radius. Sorry.
I know, but why? All right, as I go left to right, they get more electrons. But that's not I'm asking, as you go down a period, why is the atomic size increase?
Electrons are higher and higher energy levels.
Right. So everybody in right here, he only has 1 energy level, and here he has 2 energy levels, 3, 4, 5. And so in every case, as you go down the periodic table, the atomic size always increases. Is that right? So that's a trend. Now, what if we were to look at, let's see if we can find it here. Size. Here it is, atomic number. Okay. This is a great picture. All right. So as I go down, the first group, does the size increase? Yeah. And second group, yeah. Third, fourth, every group, as you go down, the size increases because you're adding new energy levels, which are further away from the nucleus on average, like that. But we have a problem. What is the what is the trend as you go left to right? So I take any period, like number 2, what's the trend of atomic size as you go left to right? And you can look at the picture here, what do you see? Now, anybody know, take a stab on that one? All right, Calvin.
Is it because, like, the more protons you add, like, the more it brings everything together?
That happened here, though. I had more protons here.
But you have more electrons. Like, I know it says more electrons, but it's like, I think you use like example of like babysitters. It's like, the more babysitters you have, the closer they can keep.
Yeah, as long as I don't let the babies get further, go to the second floor, third floor building. So if the electrons are in the same average distance from the nucleus, and I have more, they call it nuclear charge, more protons, it tends to draw all of the electrons in a little tighter. So that's not very intuitive. You would think as the number of electrons increases, that the size of the atom would increase, but it actually decreases, doesn't it? Yes.
So naturally, the energy levels would be closer together in the non-metals than in metals, right?
What happens here is they have, these are called the representative elements. That's one of the questions on the test course. But the representative elements are the ones that have the S and the P blocks. And the reason those are representative elements because the pattern's very strong and all your valence electrons are in S and P, and that's where all your chemistry is taking place. So it is true that the transition elements do, funny things a little bit. But they didn't include it here, and I'd have to go look up the actual diameters of the transition elements, but I think most of them also decrease.
So if they are smaller and the energy levels are closer together because they're smaller, does it still take?
When it's smaller and the energy levels are closer together, what does that mean?
Well, in a element from the S block, they tend to be larger, right?
Only because the 11th electron is in the third energy level.
Right. But they're still larger in respective to like a P block. Element of the
Actually,
same level,
a
right?
good question. 3s and 3p, even though the p, it takes a little more energy to maintain a p orbital, the average distance is still about the same for S and P. Their distances are similar. It just takes a little more energy to maintain a p-shaped orbital. But
Is it,
if I were to look at, remember those things called probability zones?
yeah.
I would still, the S and the P would be they overlap each other, S and P.
I mean like distance from the nucleus.
I think if you're if you're an electron in the second energy level, your average distance is about the same, whether you're S or P.
So is it just the final? Because like the orbital gets closer to the nucleus, and
I don't know about closer, but you might say that the electrons that are in those orbitals might be pulled a little closer to the nucleus. So the diameter of that might get a little smaller. So the diameter of the second energy level might get a little smaller. I guess that's how I say it.
So does it still take the same amount of energy to go from one energy level to another?
Okay, what a great question. Wow. So for example, you know what? I did look that up because he's saying here, if I went from 2p to 3s, like that, what if I went from 2p to 3s2, or 2p to, that's a great question. You're asking if it draws all electrons in a little closer, then wouldn't it also change the amount of energy it might take? I don't know the answer to that. That's a great question. No one's ever asked me that. That's a great question. I don't know the answer. I'd have to go look up some data. All right. So anyway, you know what's interesting is one of my favorite periodicity things to look at is right here, and I'll show it to you. This is called ionization energy. Okay. So I want you to think about this, and we're just learning for the sake of learning right here. Okay, and I'm gonna try to help you with the test too. But let's say I had lithium, and I had some kind of device that said I have neutral atoms in there, but I'm going to excite them. I'm going to use electricity or microwaves or heat. I'm going to excite them one way or another, and they're all neutral. And I noticed there's no charge going from the top of that container to the bottom. So my instruments show no charge. Well, then I start adding more energy, and then I get to a point where all of a sudden, I notice there's a charge somewhere inside that container. Why would there be a charge when all I had was neutral lithium atoms? What do you think might have happened? You add energy, all of a sudden, there's a charge, and they have a definition for that. It's called first ionization energy. How much energy does it take to remove your first electron? And I think this is a great pattern. This is very chemistry oriented, okay? Look at this pattern. Nobody's going to memorize that graph. And you can open the book, can't you? On the test, you can look it up. But what do you notice? Who takes by far the most amount of energy to remove one of the electrons? Who's at the top of the mountain peak here? What do you see here? Who's here? Who's here? Who's here? Who's here? It's like in every period, one of these elements, it takes way more energy to remove an electron. Who are they? Noble gases. And that's how they knew that when you have an arrangement, remember, except for helium, everybody has a stable octet. All the noble gases have 8 in their outermost energy level. And so they don't want to gain. They don't want to lose. You're going to have to almost destroy them before they're going to lose an electron. And so how much energy does it take? And this happens to be in, what is this, kilojoules per mole or something like that? What's that say? Is that J? Yeah. So kilojoules per mole. All right, this is high. Look at that guy. Hey, you want to take one of my electrons? Yeah, just try it. Yeah, just try it. It's almost impossible to get helium to remove one of his electrons. And now, it might be a little more likely, still very unlikely you're going to take anybody's electrons if you're a noble gas. What else do I notice? Who's at the valley? Who does it take the least amount to remove their first electron? Who's found at the bottom of the valley? Wow. Does that make sense to you or not? Look at this right here. Who is that guy? Oh, yeah, lithium. I don't know why I can't read that. Okay, so guess what? Hey, I want to get you to lose one of your electrons. Okay, sneeze on me. Or give me a little energy. Oh, there you go. I want to become an ion pretty badly. And what do metals have a tendency to do anyway? Lose. And who loses them easier than anybody? The alkali metals. And so I think that's really neat to watch this. And when I was first learning this, I didn't learn this in high school, but when I learned this in college, I also thought it was interesting, these little rear. What do you think that is? Huh? What do you think that is? Let's take a look at the rear. Okay. So anyway, hey, by the way, see hydrogen? It's in the same column as the alkali metals, isn't it? But it's not real low. Why? Why isn't it real low? Why isn't it down here like with these guys? What do you think? Ideas. Somebody besides Tim. Ideas. Somebody else. Gabby, you can do it. Why do you think hydrogen is not way down here like with lithium on those? Does it have one valence electron like all the rest of these? And if you only have one valence electron, you tend to want to lose it, except hydrogen doesn't really want to lose it very. And you're getting there. So how many protons are attracting how many electrons?
It's like a 1-to-1 ratio, so
Right.
it's pretty strong.
So it's actually kind of difficult. Is that what you were going to say? So it's kind of difficult to remove hydrogens with one electron. That's why we say most of the time hydrogen's +1. It would tend to want to gain one, doesn't it? But could you get a hydrogen -1 called a hydride ion? You don't hear about that very often, do you? Sodium hydride? Most of the time hydrogen's +1, isn't it? Because it would tend to more likely gain one. So let's talk about a little bump here. And I'm not going to get into every little bump, but let's take a look at that first little bump right here. What's that all about? it doesn't take hardly any to remove the third electron from lithium, right? How about beryllium? Why does it take a little bit more? How many, think about electron configuration. 4 electrons, 1 s2, what's the next one? 1 s2, 2 s2. Paired up or not paired up? Paired up, a little more stable. When you can pair up electrons in an orbital, a little more stable. If I'm more stable, I don't really want to get out of that zone, and so it's going to take a little more energy to convince me to lose one of my electrons. Let's try one more. Let's try nitrogen. Ready? I'll lose an electron pretty easily, boron says. Carbon, not bad. And nitrogen, no, quite a bit more, okay? So what's nitrogen's electron configurations? 1s2, 2s2, 3p3. Anything you remember about that? Remember, what's the orbital diagram look like? Remember, like, there's 3p orbitals, and you got 3p3. Ready to go? 1, 1, 1. And again, somebody won a Nobel Prize. I didn't. That they said a half-filled suborbital is stable. It's a little bit more stable. So I don't really want to lose one of those p electrons. So now, here's the really good stuff. To me, when I saw this, it's like, whoa, that's really good. Okay, look at sodium's first ionization energy. How many? What is this in kilojoules again? This is kilojoules per mole. Hey, I want to lose your first electron. All right, that's not too bad. 495. I'll lose it pretty easily. I'm going to take away a new electron from you, sodium. Oh, yeah? Try that. Wait. It only took about 500 kilojoules to remove your first one, and it took almost what? 4,500? What? How did it jump so big? Who knows? We're just being science people here, okay? Calvin, what do you think?
Because you went back to the completely full 2p orbital?
Say it again.
Is it because you went back to the completely full 2p orbital?
Yes, and if sodium loses one electron, right, where are the next 8? Aren't they in the same arrangement as who? Isn't that right? Oh, noble gas. No wonder sodium only wants to lose one electron, because it's really hard to make it lose 2, isn't it? Because I have a noble gas configuration. Whoa. Pretty neat, isn't it? Look at this guy, next guy. How about magnesium? Well, a little bit harder to take away my electron, because remember it's 3s2 paired up. So a little bit harder to take away my electron than the sodium. But, and how about the second one? Well, it's going to take you a little bit more, because now I have more protons pulling on less electrons, so it's going to be a little harder for you. But then when does it jump? Whoa, 7,000. You see that? Magnesium will lose one and then another one, but you want to try to take another one away? That's really hard. Does that make sense about the noble gas configuration? If magnesium loses 2, won't its remaining 10 electrons be like neons? No wonder it only wants to lose 2. You try to take away a third one, the third ionization energy would be huge. Huge. All right, anyway, is that on a Monday? Can I excite you a little bit? try to excite you a little bit here. Anyway, that's what that pattern's showing, and here's a chart actually with real numbers. I think that's pretty neat. All right. Okay. And let's do another one. Let's see if we can find electronegativity. Uh-oh, wrong way. Uh-oh. I may have to go to my packet. Shoot. Where's my packet? Sorry. Radius. Okay. Okay, why don't I have a graph of that? That's one we just looked at, first ionization energy. Okay, we'll take a look at the table here for a minute. We did this when we were doing organic chemistry. No, that was another chapter. Remember how we went way back in the back of the book and we looked at this thing called polarity? And remember how we talked about it was the difference of electronegativity? Like what kind of a bond is going to form between oxygen and oxygen? What kind of bond is forming between oxygen and oxygen? And you look up a chart, and here's electronegativity, and it's just a number that humans like to look at. I don't want 0.00051, I don't want that. So humans like to see a number like that, and say the electronegativity of oxygen is 3.5. What's the electronegativity of the other oxygen? 3.5. What's the difference? What's the difference in electronegativity? 0. That means that bond's going to be 100% what? Covalent, ionic? Covalent. Get it? What about oxygen and hydrogen? And the difference is 1.4, right? And if you looked on that chart, we looked on that chart in that chapter, and we found out that's not 100% covalent. It actually has a little bit of a tendency to be what? What do we call it when you're not 100% covalent, but you have at least some tendencies to, what's it called? Polar covalent. Remember that? And then there was some break point. I think it was, I don't know why the books don't like to print it, but I think it was what, 2 point something, 2.5, 2.7? When the electronegativity difference is greater than that, then they said, we're just going to go ahead and call you ionic. The electron's spending so much time with the other guy, you probably took it away. And so we found out that no bond's truly ionic, but some might be so ionic that they act like ions most of the time. So what is the trend here? Electronegativity says when we're sharing a pair of electrons, who has the greater ability to pull the electrons toward them? Another way of saying that is who really wants to gain electrons? Now, if you look in a book and they give you electronegativities, you will not see any values for the noble gases. Why not? Why would you not see any values? They're trying to do an experiment to say, here, form a bond, and we'll see how much you really, how much the electrons want to go toward you. And so why don't they have any numbers for noble gases? Yeah.
Because their valence electrons are already full, so they don't want to.
They don't want to share electrons. You get it? They don't want to share electrons. So the definition says if we share a pair of electrons, what's the tendency for you to pull them towards you? But what's the trend? Ready? What's the trend? Electronegativity as you go left to right in a period. What would you expect electronegativity to do? Go up or down? Who really wants to gain electrons? Who are they? The nonmetals, don't they? So when you go here, hey, I really want to gain electrons, sodium? No, not at all. I want to lose it. Hey, you want to take my electron away? Okay. I'll form an ion compound just like that. And so the electronegativity goes up as you go to the right. Now, hard question. What do you think happens to electronegativity as you go down? Wow. That's a hard question. I want you to think about this, okay? Did you ever wonder if 8 is the magic number, and if you have less than 4 valence electrons, you tend to lose 1, 2, or 3, and you're a metal. If you have more than 4, then you want to gain 3, 2, or 1, don't you? And that's where the nonmetals are. But this little stair step, I think it should be drawn right here. Shouldn't it be like right in the middle where 4 is? And everything, and this line here should be like this, and everything there's a metal and everything. Why is it stair step like? Why is it running out? Why is it Why is it angled like that? If 8's the magic number, why would you still be a metal when you have 5 valence electrons? Who wants to take a chance on that? Why would you still be a metal even though you have 5 valence electrons? All right, Tim.
Since they're lower on the table, electronegativity in general is lower, so it's more easy to lose electrons.
Why do you think that's lower?
Metal,
What about ionization energy? Who do you think has a higher ionization energy? And ionization energy means how much energy would it take to remove one of my electrons? Well, first of all, I'm not a metal. I don't want to lose them, all right? And also, I only have them in 2 energy levels, and I'm going to hang on to them pretty hard. But what happens when I get down to here? Where are your valence electrons? Way out there in the 6th energy level. See that? The 6th energy level. And if you read a book in chemistry, here's what they're going to say. Here's your nucleus with a bunch of plus charges, right? And here's the 1st energy level. And I'm drawing those circles. Is that okay? And here's one way out here in the 6th energy level. And it says, hey, don't forget about me. And they call it the shielding effect. The shielding says, what charge does this electron, this energy level have? What does it have? It's negative, isn't it? What about this one? Negative, negative, negative. And the idea is that this guy's way out there and he's being shielded from the effects of the positive nucleus by 5 other energy levels. And that makes this thing easier to be lost. And that's why it explains that even down here, that would act more like a metal, even though it had 6 valence electrons. They're way out there in the 6th energy level. Much easier to lose that. Yeah.
Isn't it kind of a paradox if the further from the nucleus, the less ionization energy it takes to lose the electron?
It takes the ionization energy to be low as you go down a group or family.
But
Lower.
Don't energy levels further away from the nucleus also take more energy to get up a energy level?
But if they already have a high energy with them, then how much more energy do you need to escape the nucleus?
It just seems
Um,
a little weird that it would take more energy to go up a level if there's such a low ionization. Because both of them rely on how hard the nucleus has a hold on the...
I think when they talk about the shielding effect, I think it's almost like as if here's a whole bunch of negative electrons here, and they would tend to repel each other, wouldn't they? And they said they shield I didn't make that up, but they said the shielding effect is that the more energy levels you have between you and the nucleus, the less they can pull on you. I don't know if you want to look that up. Who actually came up with that? Who actually came up with that idea, the shielding effect? See if you can find that, okay? And then maybe it'll answer your question there. I had one more I did want to show you. I want to see if you can figure this one out. Okay. Here's a kind of a hard question. Okay. Which one's bigger? Lithium atom, lithium ion. What about ionic? What's the trend in ionic radii? Somebody who hasn't answered yet today, what do you think? Who is it bigger, lithium atom or lithium ion? Who do you think's bigger? So somebody take a chance. All right, sit on. Is that a guess, or are you going to tell me why?
I guess.
Okay. Can you now guess at why?
Did you ask which one is bigger?
Huh?
Because it will.
Now she's starting to think. Look, I can tell. So your eyes are going back. What do I remember? What have I ever seen?
It would be smaller because they wanna lose the electron, like,
Wait, you're changing your mind now?
yeah,
Ooh, I like that.
they wanna lose an electron to become more like helium.
Wait, say that last thing again?
They wanna lose an electron to become more like helium.
Now, wanting to lose an electron means you have a low ionization energy. But what about the size of you?
Smaller,
Why?
because you're losing the energy field.
Yes. All right, so what? Look right here. Great job. Now, this has 3 electrons, right? 2 in the first, 1 in the second. And it's got to be bigger. It's got to be bigger than hydrogen because it has 2 energy levels, doesn't it? But what does a lithium ion have? Didn't it lose that 1 electron? Now how many electrons does it have in the second energy level? I'm looking at your faces. None. It has none in the second level. That's why the ion for metals, the ion is almost always smaller because they lose their valence electrons. I agree, the transition metals, they're going to have their own pattern a little bit in a way, but if I take any of these metals here, especially the representative elements, the aluminum ion is definitely smaller than an aluminum atom because the 3 electrons that he loses means he won't have any electrons in the third energy level, and that's why it'd be that way. How about nonmetals? Christine, you had your hand up. Tell me about this. A little bit harder, definitely harder. The size of a fluoride ion compared to a fluorine neutral atom. What is it?
If it was a negative ion, it would be bigger,
Because?
gained an electron.
Because? What now?
It gained an electron, it has 1 more electron.
And? Why would it make it? Can I give you a hint? If I go across period number 2, I add electrons, but the atom gets smaller because I'm also adding protons. So what makes you think, you said that the ion of a nonmetal would be bigger? Okay, tell me again.
Because it has 1 more electron.
And? See, 1 more electron can't be the answer because I have 1 more electron, I'm smaller.
It has 1 more electron and 1 less.
And?
Proton.
What? Say it again?
It's the same number of protons.
Yes.
There's 1 more electron.
There we go. All right, now, babysitting, okay? 9 babysitters are watching over 9 kids. And then you throw another kid in there. How much attention can they pay? They have to pay, that's a terrible analogy, but the theory is that if you have the same number of protons, but you add another electron, that all of them are going to be a little less strongly held. And so for nonmetals, the ion tends to be bigger than the neutral atom. But for metals, the ion tends to be smaller. Wow, you guys do a great job. Because I know you haven't read this, right? Nobody sat and read that book, did they? You guys read the chapter yet? No. Okay. So the fact that you can sit here and think about it, that's great. All right. There's one more that did I know why this picture is in here? Anybody know what's in there? Here, I'll read it to you. Setting the aluminum cap on the Washington Monument in 1884. At that time, aluminum was regarded as a precious metal. I bet some of you put a precious metal in the recycling can this weekend, didn't you? Anybody do that? At the time, they didn't know how to get aluminum out of the earth. It's a stuff called bauxite. Bauxite's an orange dirt. And no one would ever think that an orange dirt had this stuff in it. But we learned how to do it later. Later, we learned how to get it out. But at one time, it was very expensive. It was so expensive, they said, we're putting it on the top of the Washington Monument. It was more expensive than gold. But then they figured out how to make aluminum cheap, and now you guys use aluminum foil, aluminum cans, and they would not understand that if you went back in time and you were drinking something in an aluminum can, what do you have there? It'd be like somebody drinking a solid gold can. You think, what are you doing with that? I'm gonna put it in recycling. No, don't do that. Well, I just wanted to show it to you. Okay. The other one that I don't want to spend a lot of time on, but here it is. If you go to college, they'll probably talk about it. And even the data, I don't even like the graph because the graph's kind of like, wow, where's all your missing data? And it's called electron affinity. It says the energy chain associated with the addition of electron to a gaseous atom. All right, so what you have to do is you have to turn everything to a gas. You have to vaporize things. So you vaporize them, and you can vaporize metals. Whatever you're going to do is vaporize them. And then what you want to do is try to get them to take on another electron. And it says here, how much energy is associated with that? Well, it should take very little energy to get a nonmetal to want to gain an electron, right? So its electron affinity is very low. And then non-metals said, no, I don't want that. I don't want that stuff. And so I don't really want to mention that too much. They only have one little, 2 paragraphs on the whole thing. Okay. Here's a typical question that they would ask in college, and they also like ask in the book, and it's on my test. Let's take a look at this one, and try not to look at the answer. Hang on here. You're trying not to look at the answer. It says here, predict the trend in radius for the following ions. Okay, now, what I want to know is which ones are bigger. This is kind of a hard question. So, what do you think about that? A beryllium plus 2 ion, his electrons would be like...
Students, please pardon the interruption. I need to remind all Move Up Day volunteers, all rhetoric Move Up Day volunteers to please come to a meeting in the forum after you grab your lunch today. Thanks.
So any ideas, did they say biggest to smallest or they didn't say?
I think it says where it's covered.
Okay. What do you think? You want to go smallest to biggest, or what do you think the smallest ion would be? Say beryllium plus 2 means it doesn't even have a second energy level, does it? So, all right. What about magnesium plus 2? Would that be bigger or smaller? What do you think? It wouldn't have a third energy level, but it would have 1 and 2, wouldn't it? What about calcium? That's a tough one because, it wouldn't have a 4th energy level. It would have 1, 2, and 3. And what about strontium? Okay, so let's see what the book says. It says, all of these ions are formed by removing 2 electrons in an atom in group 2 elements, giving way to beryllium. So so beryllium should be smallest, and it was kind of like right in order, wasn't it? Okay. All right. I think that's about it. Does everybody know the parts of the periodic table? We did that in 10th grade, but metals, nonmetals, and even though a lot of our American books say metalloids, probably the rest of the world, they use the word semi-metals. Have you ever heard of semi-metals? The semiconductor industry, Silicon Valley, I think a lot of the world likes to use semi-metals instead of metalloids. So then we had, let's see, that's about it. All right, well, I'll tell you what I'd like to do tomorrow is I'd like to not use the book at all. We're going to do, set you up with a lab. We'll actually do a little like pre-lab thing tomorrow. I'll let you do a little tiny bit of chromatography tomorrow. And then I want you to take off, and I'll tell you the rules and what you need to do. And then you and your partners, and I will let you pick your partners. You and your partners are going to try to say, we're going to do about 5 or 6 really good days of lab and chromatography, and I'm going to do as much as I can. I'm going to provide you with a lot of different solvents. Water. Oh, thanks, Mr. Feeney. Distilled water, if you want to do that. All right. I'll have salt. You can make salt water. I will have isopropyl alcohol. I'll have 1-propanol. I'll have hexane. I even have some hexane right here. I want to show you a real quick demonstration before you leave today. I'm actually doing this for my other class, but it falls right in line here. And so what I'm going to do, I close that up and put some water in there. Oh, well. Water has a polar nature to it, And when they say likes dissolve likes, polar things tend to dissolve polar things. I have here hexane. You know what it, when you did organic, you knew how to say hexane, you knew the formula. You said, what does it look like? It looks like this. Now, methane, gas, ethane, gas, butane, gas, all right, pentane, right close, hexane, liquid. There you go. Now, when you're doing chromatography, you want things that are polar to be able to separate things that are polar. So if you use a water-soluble marker, I would tend to say water or salt water would tend to separate it better. But what about leaf extracts? When you take chlorophyll out of a leaf, water is not very good at dissolving or separating things there. So you might decide to use an organic solvent. You get that? And that's what this is. So that's what hexane looks like. And you know what? Could you do me a favor? It fell on the floor. There's a lid there. It's made out of glass. And I'm afraid I'm going to spill this. Oh, thank you. I know what you're thinking. You're thinking, we'll just do that and then they'll mix. Yeah, alcohol will, because alcohol is polar, isn't it? Alcohol has one end that's polar and one end that's not polar, but it still mixes well with water. This won't. No. Mr. Feeney, now what are you going to do with this, huh? I bet you can't get that back. How are you going to get it separated? This is called a separatory funnel. And all I had to do is the most dense material is water. See? And so the more dense material, I'm using the physical attributes of water. Slow down. That's not. Okay, I lost a little bit. That's right. Anyway, so now I can put this back in here and we have hexane. So when you're doing chromatography, you want to think about polar, non-polar. You might try one and say, hey, nothing happened. Well, you had the wrong solvent, didn't it? Tell me, Mr. Feeney. No, you figure it out. Yes?
Does surface tension still operate the same?
Does what?
The water?
Now, wait a minute now. For polar things, you tend to have surface tension. For non-polar, you don't.
But does it
But
still?
it does, what your question is, I think it is, can I still have surface tension with hexane sitting on top of it?
Yeah, with salt.
I don't think about insects floating on top or sinking into hexane and floating on top. It'd be hard for me to measure that. That's a great question. I've never read anything about what happens to surface tension of water when hexane's sitting on top of it. I've never read that. You have some really good questions today. So if you're playing Stump the Teacher, you got me. I've never read anything like that. All right, hey, thank you very much.